Hi, my name is Dongjin. I'm presenting our work, Robust Factorization of Real-World Tensor Streams with Patterns, Missing Values, and Outliers. Tensors are everywhere. Tensors are high-dimensional arrays that are effective tools to represent multi-aspect data. Data modeled as tensors are collected and utilized in various fields in our lives. In many applications, tensor data are usually collected incrementally over time in the form of a tensor stream. The tensor stream extends in the time mode and can potentially be of infinite length. Furthermore, real-world tensor streams often include missing entries and unexpected outliers due to unintended problems such as network disconnection and system errors. In this work, we answered the three questions. Given that real-world tensor streams with missing values and outliers, how can we estimate the missing entries? Can we also predict future entries? Can both imputation and prediction be performed accurately in an online manner? Traditionally, CP factorization-based tensor completion approach is widely used to estimate the missing values. CP factorization is to find the factor matrices, that is a low-rank approximation of the target tensor X, only considering the observed entries. However, the limitation of standard CP factorization are that it does not handle tensor streams and it is vulnerable to outliers. Another traditional method is the Holt-Winters method. The Holt-Winters method is very effective time series forecasting algorithm when time series show seasonality. It decomposes time series into level, trend, seasonality components, and using them, it can forecast future evolution of the time series. However, the standard Holt-Winters method does not handle missing values and is vulnerable to outliers. In this work, we propose SOFIA, a CP factorization-based streaming algorithm for real-world tensors with missing entries and outliers. SOFIA can answer all questions at the same time. Let me define the problem to be addressed in this work. Given a sequence of incomplete and noisy subtensors, the objective is to estimate missing entries in the subtensors and future values of the tensor stream. We propose a method to minimize such imputation and forecasting error. Now, we introduce our method, SOFIA. We formally define the factorization model of SOFIA. First, we consider a case where the input tensor is static. We assume a partially observed and corrupted tensor Y is given, where the nth mode is temporal and the others are non-temporal. In our factorization model, we leverage two types of temporal properties in real-world tensor streams. The first is temporal smoothness, the property that the successive values tend to be close. And the second is seasonal smoothness, the properties that the values between consecutive seasons tend to be close. To consider these characteristics in tensor factorization, we imposed constraint on the temporal vector matrix. The first and second penalty terms in the objective function encourage the temporal and seasonal smoothness in the temporal vector matrix respectively. And the last penalty term enforces sparsity of outliers. By solving the optimization problem, we can get temporally and seasonally smooth temporal vector matrix. Now we consider a case where the input tensor is dynamic. Specifically, we assume that a sequence of incomplete and corrupted subtensor yt is given. Then, at each time t, we aim to minimize the following objective function. Similar to the static tensor case, the first and second penalty terms in the objective function encourage smoothness. Ideally, we need to optimize the objective function considering all the historical data. However, this is not feasible since we are dealing with a tensor stream whose length could be infinite. So, how to solve the optimization problem incrementally in an online manner? Optimization algorithm of SOFIA consists of three steps. Let me explain each step in detail. In the initialization step, we initialize all the factor matrices by solving the batch optimization problem using a subset of the corrupted tensor data over 3 seasons. Through initialization, we can get a temporally and seasonally smooth temporal vector matrix. The overall procedure of the initialization step is as follows. The input is a batch tensor y_init. The factor matrices are randomly initialized and the outlier tensor is initialized by 0 tensor. Then, 3 tasks are repeated until the factor matrices converge. First, reject outliers from the input tensor. Next, update the factor matrices by SOFIA ALS, which is the ALS method to minimize the objective function in the batch scenario. Lastly, update the outlier tensor by applying the element-wise sub-thresholding with the threshold lambda 3, which is a hyperparameter, to the residual tensor R. It means that residual is regarded as an outlier only when the absolute value of the residual is greater than the threshold. By repeating these tasks until the factor matrices converge, we can finally get factor matrices and an outlier tensor. Note that the temporal factor matrix is temporally and seasonally smooth. In the second step, we feed the Holt-Winters model to the temporal factor matrix. Each of the column vectors of the temporal factor matrix can be thought of as seasonal time series of length 3m with period m. By feeding the Holt-Winters model to each column, we can capture level, trend, and seasonality components of the temporal factor matrix. Moreover, using the Holt-Winters model, we can forecast the next temporal factor vector. In the last step, we repeatedly observe a newly arrived subtensor and update our model robustly to outliers using the captured temporal patterns in the previous step. At time t, we receive yt and have the previous estimate of the non-temporal factor matrices and the previous m estimates of the temporal vectors. Through the 5 tasks, we can update our factorization model and input the missing values. First, estimate the outlier subtensor OT. We can predict the temporal vector by one step ahead Holt-Winters forecast, and using it, we can predict the next subtensor to be received. Then, we regard the prediction error as an outlier only when the prediction error is significantly large. Specifically, we apply the 2 sigma rule to filter out the small outliers. Next, instead of considering all the historical data, we focus only on the current input subtensor yt and reformulate the objective function like this. Then, we update each of the non-temporal factor matrices by one-step gradient descent. Next, we update the temporal factor vector by one-step gradient descent. After updating the factor matrices, we update the Holt-Winters model with the updated temporal factor vector. Through this, we can obtain slightly updated level, trend, and seasonality components, which will be used at next iteration. Lastly, we can reconstruct subtensor xt hat using the updated non-temporal factor matrices and temporal factor vector, and estimate the missing values on yt using the reconstructed subtensor. In summary, through 3 steps, initialization, fitting the Holt-Winters model, and dynamic update, SOFIA accurately estimates the missing values in corrupted tensor streams in an online manner. Now, let me answer the question, how can we predict future subtensors? We can forecast future temporal vectors by applying the Holt-Winters forecasting method. Then, given any time t, we can forecast future subtensors using the most recent non-temporal factor matrices and the predicted temporal vectors. Let me share experimental results. We performed experiments on 4 real-world tensor streams. We used a tuple of x, y, z to denote the experimental setting. X and y represent missing and outlier ratios among the entire entries respectively, and z represents the magnitude of an outlier. We show how precisely the initialization step discovers temporal patterns in an incomplete and noisy tensor. Here, there was a synthetic seasonal tensor. We corrupted the synthetic tensor, and we extracted the temporal pattern from the contaminated tensor using 2 methods, the vanilla ALS and SOFIA ALS. Initialization with the vanilla ALS could not capture the meaningful pattern, while initialization with SOFIA ALS was able to restore the temporal factor matrix accurately as iteration proceeded. This is because temporal and seasonal smoothness considered in SOFIA LS are greatly helpful to find the underlying patterns. We measured how accurately SOFIA estimates missing entries. SOFIA was the most accurate regardless of the degree of missing data and outliers. This is because SOFIA discovers temporal patterns behind the noisy and incomplete data and accurately predicts the entries in the next time step using the Holt-Winters method. Based on the predictions, SOFIA filters out outliers, and thus SOFIA is robust to outliers. This figure shows the overall imputation accuracy over the entire stream. SOFIA gave up to 76% smaller imputation error than the second most accurate approach. We measured the average running time to process a single subtensor of different approaches. SOFIA was greatly faster than the second most accurate algorithm. We evaluated the forecasting accuracy of SOFIA. Since the competitors do not take missing values into account, we evaluated them assuming all entries are observed, while SOFIA is evaluated on various fractions of missing entries. As seen in this figure, in all the tensor streams, SOFIA was the most accurate despite the presence of missing entries. Lastly, we measured how the running time of SOFIA scales. The results show that SOFIA scaled linearly with the number of entries and the number of time steps. That is, the time taken by SOFIA per time step was almost constant regardless of the number of subtensors processed so far. In conclusion, we propose SOFIA, a streaming factorization algorithm for real-world tensors with missing entries and outliers. By smoothly and tightly combining tensor factorization, temporal pattern detection, and outlier rejection, SOFIA achieves the three strengths here. Thank you very much for attending our presentation.